To develop this project, it was necessary to know about the operation of pumps with viscous fluids. When a centrifugal pump is used to pump high viscosity fluids, its behavior changes dramatically. This is due to the losses that occurs inside the pump. When this happens, the performance of the pump is estimated with some correction factors for the flow head and efficiency according to the Hydraulic Institute. Since volumetric flow rates of water were already known, the first step was calculate the B parameter in the best efficiency point of the water with the equation 1. After this was calculated, since B was into 1 and 14, the next step was calculate the correction factor for the flow. Having the correction factor of the flow, that is equation 2, for the rest of the volumetric flow rates were calculated with equation 3. Also to find the head of the best efficiency point of the viscous fluids with the equation 4 and 5. Having the volumetric flow rates of water and the correction factor of the head at the best efficiency point, the head correction factor was calculated with the equation 6 and 7. To continue with the process, the correction for the factor efficiency needed to be calculated with equation 8 and 9, and finally the input power was calculated with equation number 10.
Table 1 shows that the fluids given can be classified in 3 categories based on the kinematic viscosity of each one. This will present different patterns.
This figure shows the total head curves for each fluid. First, the total head in the shut-off condition is the same for every fluid. This means that at this point, the pressure increase is independent of the fluid properties. Second, it can be easily identified the 3 categories mentioned above. This is due to the high differences of kinematic viscosity, since higher viscosity results in a bigger shear stress needed to move the same volume of liquid. In addition, it must be noticed that as the kinematic viscosity increases, the volumetric flow rate in the algorithm is reduced. This is owing to a bigger slope in the total head with higher viscosity values. Talking about the efficiency profiles, these have similar behavior. Despite this similarity, the magnitudes of the efficiencies have great differences. For instance, for water and its equivalents, the best efficiency point is near 20%, while for the most viscous substances, it is around the 0.45%. This is the consequence of the viscosity effect, since more losses produces less hydraulic power.
For the CFD simulations, they were chosen 3 fluids, 1, 2, and 7. The graphs of head efficiency, brake power, and hydraulic power are shown below. These fluids were chosen because they were the ones whose kinematic viscosity was separated, and taking into account that high viscosity fluids would have given a negative head. It can be seen that the head had always a linear behavior and the efficiency had always a parabolic form, where it can be clearly seen the best efficiency point. Also, in the graph of the total head of fluid 2, it can be observed a negative head. This could be explained by the high viscosity, which exerts a force over the impeller bigger than the one the impeller applies on the fluid. On the other side, it can be seen that the brake power also has a linear tendency and the hydraulic power has a parabolic tendency. Following the HI algorithm, it is evident that between fluid 1 and 7, where 7 has a bigger viscosity, the head decreases, and finally in the power, it is also evident that the data behave as it should, where power increased.
Following graphics can be observed that the brake power tends to rise if the volumetric flow rate does, since more liquid is needed to be transported. It's worth mentioning that since the B parameter in these fluids was higher than expected, causing the values obtained with the HI algorithm not to be exact. Additionally, it was expected that the kinematic viscosity increased, so did the need for power. In the following table, the Reynolds number for the fluids were presented, in which the regime went from laminar to transitional regime. A turbulent flow was assumed due to the geometry of the volute. In the following graph, it can be seen that the Reynolds number increased, the head in the best efficiency point also increases. If 2 or more fluids have the same viscosity, its Reynolds number will be very similar, and the head of the pump operating with this fluid will be similar as well. If the viscosity remains the same but the density varied, then the kinematic viscosity will vary too. The volumetric losses are caused by some leakages, which decrease if the viscosity increases, causing the Reynolds number to decrease.
In the shut-off, HI results on constant total head without regard to kinematic viscosity, while in CFD total head depends on it. This can be explained by the fact that in HI characteristic properties are estimated from water behavior using a correction factor to obtain the characteristic curves. For total head, it is a more accelerated decline for those fluids with major kinematic viscosity, whereas in simulations the curve is also displaced to smaller numbers. This could make sense if it is thought that when the fluid rate is 0, the behavior depends only on the pump and its specifications. However, CFD simulations are never run with mass flows of exactly 0, which means that at least a drop of the fluid is simulated, then the fluid properties do matter. This figure is made to show the difference between the results obtained in CFD and HI. It can be observed that the methods used provide similar results on the best efficiency point as the regression coefficient is close to 1, yet not enough. In this way, can be concluded that HI algorithm is useful to give a basic notion of the behavior of the pump without high accuracy.